So your research group recently collaborated with researchers at IBM to create a chip that you guys call True North, and that the press has been calling the brain chip because it's inspired by the structure of the brain. So I guess if students want to go find this project, they can probably Google brain chip, and they'll find it. Now this is not a von Neumann architecture like we're teaching in the course. Can you describe this chip in terms of how it differs from a von Neumann architecture and how it tries to mimic the brain?
Sure. So I mean, I'm not sure I want to get into sort of von Neumann versus not von Neumann because different people interpret that in different ways. But I'll talk about sort of what's the difference between that and sort of a traditional CPU and sort of explain why we designed it that way. So sort of the traditional CPUs today, there's a big bottleneck, right, which is to get data from the memory to the processor and back. So that's sort of everybody calls that the von Neumann bottleneck, right? So because originally that was sort of the idea of the stored program computer, you put everything in memory and then you operate on it. Of course, if you look at a CPU today, it's gone well beyond that. So with lots of parallel cores and so on and so forth. But that's the basic idea. Now, the problem is the cost in terms of both energy and performance. A lot of the cost we're paying today has to do with moving data around and storing it in this memory and moving it from the memory, getting it to the CPU to start doing the operations and then moving back. I mean, the computation itself has become essentially free relative to the communication costs. Right? That's where we are today.
And when you say cost in terms of, for instance, energy?
Energy is the metric I normally, when I say cost right now, I'll pretty much be referring to energy primarily. Right? Because energy has become sort of the first order limiter of the system. So moving sort of data back and forth is very, very expensive from an energy standpoint. Now, before I say anything, I'll tell you that no one really knows how the brain computes, right? So, however, neuroscientists have various hypotheses. And so the way I like to think about the chip we built is we basically implemented something that corresponds roughly to what a lot of computational neuroscientists think is happening in the brain. So what does that look like? So what it looks like is, our brain has neurons and synapses that are connected in very complicated ways. Right? So, and the other part of this is that the way things, so a neuron, depending on who you ask, can be viewed as a very simple device. One way to think about a neuron is it's got a bunch of inputs. Those inputs, the inputs that arrive on all the inputs that arrive sort of update the internal state, normally sort of adding or subtracting from a value that's stored locally. And then once that state exceeds a threshold, it produces an output. Right? And that's referred to as a spike normally. And this spike is then sent to a number of other neurons, and then the similar sort of operations keep going. And so that's how the computation proceeds. So what's interesting about this model is all the neurons are parallel. Right? So everything is inherently parallel. Right? There's no explicit memory like the von Neumann model. But there's implicit state. Every neuron has a little bit of local memory, if you want to think of it that way. So there's implicit local state. And it's all parallel. Everybody's accessing the local state. And the only way sort of state information is exchanged is through these spikes, right? Which you can think of as messages from one part of the system to the other. So that's essentially how the whole system works. So sort of everything is very naturally parallel. Everything is running at actually a very low frequency, right? So timescales that people care about are typically in the millisecond regime rather than the nano or picosecond regime. And so things are slow, and there's a massive amount of concurrency. That's sort of what the system looks like. And so that's why it's very, very different from this notion of a von Neumann architecture where you have this one little CPU or collection of CPUs which are really, really fast, chunking on data, and then the data is moved back and forth from a big memory. Right? That's sort of what happens in the von Neumann. So that's why it's so different. And so what we ended up building in True North essentially is something that can execute this sort of very parallel collection of neurons and synapses and connections.
So there's this very low frequency. I mean, each of these are not clocked by a global clock, right? There's this kind of very low frequency 1 kilohertz clock that runs, and then in between these very long cycles, everything is event-driven and asynchronous. So it uses your asynchronous design techniques.
Yeah, in fact, actually, one of the nice things about the funny things about this project is actually we used the design tools I wrote to design the chip. So you can imagine how hard it was to convince a major company to do that. But anyway, that's a long story. But at the end of the day, yeah, so that's how it essentially works. So there's this one, so the way True North works is there's this 1 kilohertz sort of tick. That's sort of the biological timescale of a millisecond, right? And the reason we have this tick is that there are a number of reasons. One of them is it actually makes it very, very easy for us to ensure consistency between the chip and the software model for the chip, which means that we could have people start mapping applications to the chip before the chip was designed, right? So that was nice. The other thing is when a spike goes from a neuron to another neuron, I mean, it goes through these axons and dendrites and synapses and so on and so forth, and there's a delay, there's a latency. And for certain applications, that the latency really matters, is used for computation. And so our True North actually allows you to have a programmable delay on a communication link. And that programmable delay is also controlled by this tick, right? So you could have 1 millisecond delivery, 2 milliseconds delivery, 3 millisecond delivery, so on and so forth. That is the granularity at which the delays are supported. So so that's the other reason for that tick. But between ticks, everything is asynchronous. The spikes are communicated across the chip asynchronously. The neuron updates are also sort of self-asynchronous. Everything's happening asynchronously until the next tick. So essentially, tick shows up, spikes get delivered at that time. The spikes for that tick get delivered to the neurons on the chip, and then all the neurons update their states and send messages they need to, so on and so forth. All of that's asynchronous until the next set of spikes get delivered. Right. So normally, if you look at the way True North runs, there's usually a burst of activity and then a lot of waiting for the next tick.
Now, from the numbers I've seen from your papers, so the chip can achieve several orders of magnitude better power efficiency than a conventional design for certain applications.
Right.
So what are the particular applications that this chip is really good at?
Right. So the main thing this chip is good at is, I would say, is the task of just the general task of classification. So classification is actually a pretty broad problem. So what do I mean by classification? So, for example, we're looking at a movie, and you want to know, is there a car in this movie, in the video I'm just watching? Is there a car? Where is it? Or, is there a person walking on the street? Where are they in this image? Right. So that's the sort of tasks that we sort of design True North for. Part of that is because our visual system does this very, very well, right? We still don't know how we still don't know how we do what we do, right? So and doing that sort of in a conventional sort of computer vision algorithm is very computationally expensive. In fact, when you take a picture of something on your smartphone and you do image processing on it, there are many cases where that actually just gets sent to the cloud for processing because there isn't enough battery or on your smartphone or even compute capability to do it in a reasonable amount of time. And so the idea was, we would pick the domains where we know that traditional compute has challenges, and this was probably a domain that we picked for True North.
So where do you, in the future, looking forward, if you develop these systems further, where do you expect to see them appear? Where do we expect that? Will we find them in the cloud to do certain types of problems, or do we expect them in image recognition systems, or
right?
Where would we see these chips in the future?
I think there are a lot of places where, well, first of all, I should say that this is like the first step. I mean, there's a lot more you could do in this domain and do a better job than what we did with True North. Even though the numbers look really good, a lot of that's coming from architecture, the overall system organization, and we can do even better. So there could be improvements on that before it ends up, being commercially successful. But on the commercial front, I can imagine a number of different domains. I mean, smartphones are a great example. You can, there are plenty of things where you take a photograph and it sort of, tells you various things about the image you've taken. Those aren't that efficient. You could imagine doing that actually on your smartphone, and maybe that's not that important in the U.S. because we've been spoiled, and we have 4G, high bandwidth connectivity almost at all time. But imagine you're in a part of the world where you don't have broadband where you are, right? Right now, that none of these applications are accessible to them, but they would be if we had this on the phone itself. And then another way to look at this is if I look at sort of data centers, for example. I mean, a lot of the sort of the processing of images and things like that is done in the cloud today, but the data centers actually use a huge amount of energy, right? I mean, the data centers are like a small city, right? So that's sort of the statistic everybody likes to use. But there's an opportunity here, So today there are data centers that have GPUs built into them for acceleration of certain kinds of operations because people are getting very, very good at using GPUs to speed up a number of different applications. You could imagine these being similar. You could have sort of the neuromorphic or true north sort of brain-inspired architectures sitting as co-processors, just like GPUs are sitting in a data center even. And when you upload your picture with Instagram or your favorite photo sharing application, when you upload it to the cloud, the processing could be done with that for much, much less energy. The motivation there isn't really performance. You can throw as many CPUs as you want, but your power bill might be significantly lower if you used these sorts of chips than just generic CPUs. So that's an application where you do it for power, not because you don't know how to do you can still solve the problem. It just would be more efficient.
Right. You need a lot more resources to do this conventionally, and like you say, power is very, very important. Very, very high cost in a data center. So
exactly.
You can do this
it's
much
like
more
most
efficient.
of the cost of the data center now is your power bill, I believe, right? I don't know if it's, yeah. But one of the funny things about True North, somebody asked me about this when I was giving a talk about it, is that they were like, so where's your cooling for this chip? Because everybody sees GPUs and CPUs with these big heat sinks and fins, right? But that's because they're just, those GPUs are dissipating 200 watts or 100 something watts, depending on which one you look at. And True North dissipates 70 milliwatts. So, you don't need a heatsink. But, it's funny because people are so used to, image processing, you're going to need lots of CPU and lots of compute and lots of heat's going to get generated. But actually, it doesn't have to be that way.
Right. So this would actually make it, because of that low power, you could integrate within a smartphone, within that form factor, not worry about the heat dissipation and battery life because of lower energy.
Exactly. That's the idea. And in fact, today I would argue that sort of cameras have become the new sensor, right? We all have one on our phones. I mean, and because of that, they're incredibly cheap and very high quality, actually. And so anything I can see, in principle, I should be able to extract from an image, right? So, I'm having this conversation with somebody who's interested in smart parking, right? So you want to know how many cars are parked in the parking garage. And everybody's trying to, you can build these nice sensors so that when a car goes over it, it knows that the car has entered a parking space and so on and so forth. But, it's just cheaper if you could take the video feed from the security camera and count the cars. Right? They're already there, the cameras. So, so there's very interesting things where, there's a much simpler solution to, counting cars, but it's special purpose. Whereas the camera's already there, and anything you can see, if you can do with it, then you'd be in a very different place. So that's another reason why I think these chips are interesting, because cameras are just ubiquitous now.